Okay, this is the next lecture in statistics and probability. This is called Chebyshevs, pronounced Chebyshev. It's a Russian name, so the name is actually not spelled correctly, but we don't use Russian letters, so we can't spell it correctly. Chebyshevs inequality, applications of mean and variance. So we've just been talking about the mean and variance of a random variable, and we're going to continue talking about that. This is going to be kind of a case where we can use it for something. We've already used it for some things, but okay. So we're going to be asking questions like, we're going to have some random variable, and we're going to say, what's the probability that it's in a certain range? Now, we've been asking those kinds of questions already, but we're going to be able to we're going to come up with an answer that's true for every random variable, which sounds strange because it's not exactly clear what I just said, but basically we're going to come up with statements that are true for all random variables. Okay, let's take a look at this. So we talked about already in the previous section, we discussed a pharmaceutical firm that's planning to package aspirin. They want to get 10,000 aspirin into each container, and we let X denote the number of tablets packaged. And we observed that the firm would want the mean of X to be 10,000. So we want to have, on average, 10,000 aspirin in each box. And secondly, we want the probability of obtaining values of X close to the mean to be high. In other words, we don't want to have a lot of variance in the number of aspirin that's put into each box. I don't want to have 0 aspirin in one box and 20,000 in the next, even though the mean of that might be 10,000. That's not good. So I want something where each box has very close to 10,000. So we're going to focus on the second criteria here in this section. So first they say that it's not good to package too many. It's not good to have more than 10,000, and it's also not good to have less than 10,000. So they say you end up if it's over 10,000, if X is much greater than the mean, then you're giving the customer more aspirin than they paid for, and if X is less than the mean, then you're losing money. So you don't want either of those. So the first approach would be recognizing that no machinery is perfect. The pharmaceutical company may settle on a certain error that it feels is tolerable. For example, they might say they could be plus or minus 10 aspirin. So then they're saying that basically anything in this range would be okay. But if they're strict about this, then of course sometimes it's going to go below this, and sometimes it's going to be above that. So they say, unfortunately, even this relaxed requirement may be too stringent. Occasionally, for example, aspirin may chip and disturb the counting mechanism, or still other unforeseen problems may occur. Recognizing this fact, the firm may relax its requirements still further and require only that the conditions of 1 hold most of the time. For example, at least 95% of the time. So we might say this doesn't have to be true 100% of the time, that X has to be in that range all the time, but we want X to be in that range most of the time, say 95% of the time. This requirement can be formulated mathematically as follows. If X denotes the number of aspirin packed in a container, and if this means what? Denotes that the probability that X is between here and here, inclusive. What does inclusive mean? means you're including, you have the equal sign here and the equal sign here. So that means including 990 and including this bound as well. Then this probability should be at least 95%. So we would say that this should be greater than, the probability that it's in here should be greater than or equal to 95%, which is what we've written here. Okay, now we're going to come to this theorem by Chebyshev, and we're going to need to refer to the mean of the of our random variable and the standard deviation. We're going to use this. Of course, we could use the expected value of x instead of this. We're just going to use this. Statisticians often find it convenient to measure the distance from the mean in terms of standard deviations, or what we can call sigma units. So let's take a look at that. So here we have the values of our random variables. So this x is our random variable. It can take on different values, and suppose that this is the center of it. In other words, this is the mean for our random variable. Then remember that the standard deviation is a number that we can calculate. It's the square root of the variance, which we can calculate. So we can talk about distances, like here's the mean and here's a. We could say, well, it turns out that a is 2 standard deviations from the mean. Okay? Or we could say that b is 1, 2, 3.5 standard deviations from the mean, or we could say that it's 3.5 standard deviations below the mean in particular. So they say, in general, to say that a point is h standard units from mu, which I guess is what, this one here. Well, they don't have h, but means that its distance is from mu is h times sigma, right? That's clear, right? Okay, let's look at the example 1. So in other words, suppose that we're told that we have a random variable whose mean is 3, or whose expected value is 3. And suppose we're also told that the variance, sigma squared, is 25. Now they ask, how far to the right of mu is the point x equals 9? Well, mu is 3, and x is equal to 9, so obviously it's 6 points to the right, but that's not what they're asking. They're asking how many standard units is it above 3. But how big is the standard unit? The variance is 25, so the standard deviation of the standard unit is the square root of that is 5. So we're saying in units of 5, how far is 3, or how far is 9 from 3? So how do we do that? We take x minus mu, that is 9 minus 3. We get 6, and we say how far is that in standard units? That's just 6 divided by the size of a standard unit, which is 5. So it's 6 divided by 5. So it's 1.2 standard units above mu. And so the formula we just used was we took x minus mu, that is we took 9 minus 3, and we got 6, and then we divided by the standard deviation, or the size of standard unit, which was 5. So we did this formula, we got 6 over 5, and this gives us then, if we put in an x, this tells us how far x is in standard units from the mean. And now comes the interesting theorem by Chebyshev, and it's going to tell us, if we say, okay, if we talk about, say, going 2 standard deviations above the mean and 2 standard deviations below the mean, Chebyshev's theorem will say there must be most of the, it will tell us how much of the data, I guess I have to say that again. Chebyshev's theorem will give us a minimum amount of the data, or a minimum amount of the probability. Let me say it in terms of data. It'll tell us a minimum amount of data that must be between here and here. Maybe all of the data is located just between here and here, just between -1 standard deviation and +1 standard deviation. But Chebyshev's theorem will say, well, there has to be at least, if we say -2 standard deviations up to +2 standard deviations, Chebyshev's theorem will say there has to be at least a certain amount. And if we go -3 standard deviations up to +3 standard deviations, Chebyshev's theorem will say no matter what the random variable, there must be at least a certain amount within those within 3 standard deviations of the mean. Now you can see obviously that the amount that has to be within 3 standard deviations can never be is going to be more than the amount that has to be within 2 standard deviations. But anyway, the Chebyshev's theorem will tell us will give us a minimum. It'll say there has to be at least this much between, at least we can say, I'll just say at least this much data between here and here, or at least this much data between, say, 3 standard deviations above and 3 standard deviations below. So here's Chebyshev's theorem. It says for any random variable, doesn't matter what it is, it's kind of powerful because of that, having a mean mu, so if we call the mean of it mu, and if we call the standard deviation of this random variable sigma, the probability that this random variable will take on a value within h units, so h could be within 2 units, within 3 units of the standard of the mean, within 4 units, whatever, but h, within h units of the mean is at least, so it's going to say it's at least something, and it's at least this. So like I said, if it's 2 standard deviations above and 2 standard deviations below, then what does it say? Then h is 2. So what does this give me? This is 1 over 2 squared. That's 1/4. So that's 1 minus 1/4, which is 3/4. Chebyshev's theorem says that there has to be at least 75% of the data, or 75% probability that things are between here and here. Okay, if I want to know between 3 standard deviations above and 3 standard deviations below, then h is 3. What do I put in here? I get 3 squared, I get 9, I get 1 over 9. 8/9 of the data has to be between here and here. So that's what Chebyshev's theorem says, and it doesn't matter which random variable it is, it says it's always true. So they say, note that this result depends only on the mean and standard deviation of x, not on the specific distribution of x. In other words, not on the probability, how the probability of x is distributed. Could be any kind of distribution, doesn't matter. Doesn't matter what x is. Okay, so if we want to write this symbolically, what we're saying is that the probability that x is mu plus h sigma and mu minus h sigma, so that's that x is between, remember it could be like mu minus 3 standard deviations up to mu plus 3 standard deviations, or mu minus 2 standard deviations and mu plus 2 standard deviations. But whatever, the probability that x is in this range will be greater than or equal to this. Okay, so this is the statement of Chebyshev's theorem. And Chebyshev was Russian, and this is a very powerful theorem because it doesn't depend on x. It doesn't depend on what random variable we're talking about. Let's read who was Chebyshev. I don't know how to say his name. Lived between 1821 and 1894. Was one of the most distinguished Russian mathematicians. He served most of his life as a professor of mathematics at the University of St. Petersburg. In addition to his work in probability and statistics, he made important contributions to the field of number theory. He solved basic problems in the construction of geographical maps and devised a way for mechanically linking bars to rectangular motion. I don't know what that means. Okay. This theorem is called Chebyshevs inequality. We omit the proof of this important result and concentrate instead on some of its applications. So you can find the proof of Chebyshevs theorem, I'm sure. We're going to go to example 2 now, which is an application. So actually we already did this. From Chebyshevs theorem, the probability that a random variable takes on a value within 2 units of two standard units of the mean, that is h equals 2, will be it has to be at least 1 minus 1 over h squared, 1 minus 1/4, 75%. So here's a picture of what we said, and what we're saying is that 75% of all the values are expected to fall in this interval. Okay, let's stop this one here, and then we'll come back and tackle the rest of this section.